Hi, my name is Minji Kang, and this is my presentation for Physics Lab 1, Constant Velocity. For the introduction portion, the purpose of this lab is to compare the position of the object moving at a constant velocity, both experimentally and computationally, demonstrating Newton's second law. Constant velocity means that the net force acting on the object must equal zero. I chose a pepper shaker to be the object for the experiment. I used the tracker app for the experimental model and GlowScript for the computational model. The main result of the lab was that both models showed constant velocity as indicated by a linear relationship between position and time. The fundamental principles in the experiment are Newton's laws. Newton's first law states that the object at rest will remain motionless and an object in motion will continue to move at a constant velocity unless a net external force is added. Newton's second law states that the net external force applied to the object is directly proportional to the rate of change of momentum of the object. We can use the momentum principle, which is also known as Newton's second law, to derive the momentum update formula and then the velocity update formula from there, which will be used for the observational model. We can also find the position update formula from the average velocity formula to measure the new position of the object as it's moving at a constant velocity. This is the lab procedure for the experiment. First, record a video of the pepper shaker rolling in a straight line at a constant speed, then import a video into the tracker app to measure the change in position of the shaker at set time periods, create a computational model of the object moving in a straight line at a constant speed using GlowScript, and input the data into the started code. Plot the data from both experimental and computational models to compare the results of the experiment on a position versus time graph. The system of the experiment is pepper shaker, and surroundings are everything else, including friction, air resistance, applied force, gravity, etc. This is the observational model. Each red marking on the visual represents the different positions that the tracker app tracks as the object moves. The graph on the right is a position versus time graph, and as you can see, it displays kind of a linear slope, which indicates the object's constant velocity during the experiment. The total time for the experiment was 2.03 seconds, and using the first two data points, we can determine the initial position and velocity. With the initial position and the next time increment and position, we can calculate the initial velocity. I subtracted the second position by the first position and divided by the time difference between the two, also known as delta t, which was 0.033 seconds. And the initial velocity came out to be negative 0.5267 for the x component. So for the computational model, we plugged in the values used in the experiment to the startup code in GlowScript. The ball mass was 1, and if the net force is 0, then mass cancels out, so mass would not affect the outcome of the model according to the velocity update formula. For the ball position and velocity, I entered the values I calculated in the last slide. Delta t was 1 over 30 because the camera catches 30 frames per second. I changed the time to 2.03 for the end time of the experiment. The net force remained 0 because the experiment was based on constant velocity. And these were the updated formulas for velocity and position. The GlowScript graphs show a linear slope on the position versus time graph showing constant velocity, and constant velocity can also be illustrated in the velocity versus time graph since there is no change in the slope and is straight throughout. With data comparison, there is a slight difference in the data sets. The blue line represents the computational model, and it appears to be more straight and constant compared to the red experimental model line because no external forces are acting on the computational model. There are a couple of deviations that could have been made throughout the experiment. There could have been external forces like friction, air resistance, or gravity, human tracking errors like camera angle, not clicking the center of the object in every frame, or rounding numbers during calculations. And technology errors like mistakes in getting even or equal increments, calibration error, or just blurred footage of the experiment. Additional questions: what if the axes were inverted? Although the slope of the graph would remain the same, the direction of the slope would change. So if the slope was originally positive, with the x-axis interchange, the slope would become negative. Is the net force really zero? No, because there are external forces like friction and air resistance acting on the object. We also cannot measure how many other forces are being applied to the object.